Okay, this is the last one for this week. There are going to be three basic concepts that are the same idea, but they'll have slightly different equations. So make sure you write those down, and so you'll label what's going on with each of them, so you'll be fine. But basically, you can do an experiment that anytime you have an electric current that goes through a wire, it creates a magnetic field. So the moving charges there create the magnetic field. And how strong the magnetic field is really depends on the following equation. B, which stands for the magnetic field, is equal to mu 0, it's a constant, times I over 2 pi r, where mu 0 is called the permeability of free space. It's not the permittivity of free space, that was epsilon 0. And that's 4 pi times 10 to the minus 7, and the units of that are Tesla meter per ampere. It's really just a converging factor between amps and meters to get to Tesla. I is the current, R is the distance away from the wire. It's kind of, you think of it like cylindrically as like the height of it is the wire, and then your distance away from the wire, the radius kind of from the center of the wire. And we're going to use the right-hand rule. It's going to be a slightly different version of the right-hand rule. This one you're going to take your thumb and point it along the direction of the current, and then if you curl your fingers around, you'll be able to see the direction of the magnetic field. And basically what it's going to be is something like this. The current's going in one direction, it kind of curls around clockwise. If it comes back out the other direction, it'll go counterclockwise. So you put your thumb in the direction of the current and your fingers curl around in the direction of the magnetic field. All right, but then, so using that result, so this let me go back real quick. So each wire creates a magnetic field mu 0 I over 2 pi r. And the direction of it's given by the right-hand rule. So if we take that, if we have two wires, we know that one wire creates a magnetic field, and then that magnetic field exerts a force on the current. So basically what happens, one wire creates a magnetic field, and if they're going in the same direction, because of the direction, the magnetic field and the direction of the force, they're going to attract. And then if they're in opposite directions, they repel. You can actually hear this if you've ever had an MRI. When it makes a lot of noise as the current's ramping up, those wires are basically kind of contracting, and then there's the opposite effect for the magnetic field. So wire 1 creates the magnetic field, and I'm going to call that B1 for wire 1 is mu 0 I1 over 2 pi times the distance between the two wires. So it's not just the generic R. I'm going to say there's a specific distance between the two wires. Sorry about that. And then that magnetic field exerts a force on wire 2, just ILB. So if we look at the force per length, usually this kind of comes in terms of the force per unit length, it's mu 0 I1 times I2 over 2 pi d. So that result, that's when you have two wires that are parallel. It's going to be an attractive force when the current's going in the same direction, a repulsive force when it's going in the opposite direction. All right. It turns out when you have a loop of wire, you take that where at the very center, you're going to get a magnetic field equal to mu 0 I over 2I, over 2r, where r is the full radius of the loop, not just some generic distance. It's at that center point, and then the pi gets canceled out because of all of the magnetic field that you're adding up. So basically what's happening is the current comes in, and it loops around, and you ends up adding up all together at the center there. Then if you have a bunch of loops of wire, that's going to add up more and more and more. And that's what it kind of looks like. Inside it gets very compact, and outside it gets very weak. So this is called a solenoid. This is what you do to make a very, very strong electromagnet. basically, when you have that solenoid, each turn of the solenoid creates a magnetic field, mu 0 I over 2r. And it cancels out outside. We're going to assume this is an infinitely long, infinitely dense solenoid. In reality, we don't have that, but we can actually treat it that way, where the magnetic field is mu 0 times the number of terms per meter times I. So little n is n divided by L. I know it looks like a 1, that's just kind of the font, I need to fix that. Where n is the total number of loops and L is the length of the solenoid. So it's the kind of the density of the loops of wire. So the more densely packed they are, the stronger the magnet's going to be. And the last thing I want to talk about real quick, it's kind of the generic idea. So if you've ever done anything with just regular alnico or steel magnets, normally in iron, nickel, and cobalt, each individual atom has a magnetic field. And in just a normal piece of iron, so imagine the top is a normal piece of iron, all those individual magnetic domains are pointing in all given directions. You know, some are together, some are against each other, some are canceling out right next to each other. But in general, they add up to 0. But in a permanent magnet, those domains add up, or some fraction of them add up. The net is in one direction or not. So each individual small portion of that piece of iron, nickel, or cobalt acts like a magnet. And sometimes they cancel out, sometimes they add up.